right, so good afternoon, everyone. We're going to be doing lenses this afternoon. We're going to be finishing up lenses and ray diagrams. So this is going to take us through probably like 75% of the light syllabus, and it's going to help us finish up a little quicker and faster. Again, this is recorded, so you all please refer to this anytime you all have questions or you have any issues that you want to, resolve on your own. So reading from our handout, we have, hopefully everyone can see this clearly. All right, so reading, one of the most widely used applications of refraction is that in lenses. A lens is an object used to redirect the passage of a light ray. They can bring rays together or make them diverge. A lens can be thought of as a series of prisms, where at the center of the lens, the prism acts like a rectangular block of glass that does not make light change any direction. At the edges of the lens, the angles of the prism mean that it makes light deviate more. So what a lens is, we basically have something that changes its size and shape and angles. I'm zooming in here so you can see how when light enters it, it changes its angle. Anybody want to tell me what is a normal again? Anybody? Nobody? All right, so your normal is an imaginary line drawn at 90 degrees to your surface. So depending on where your surface is, your 90 degrees is going to change at that point. So this is why we use lenses, because at a curve where we can draw this normal exists at different points. So it allows the light to get refracted at different angles. So this is why we use lenses. If you all can see here, it's going to bend at different angles depending on the curvature of the lens. So here what we do, if you look in the middle of a lens, if you were to cut it up into many small parts, as an infinite small parts, the very middle of a lens, it is flat in the very middle of your lens. We're not talking about, that your lens actually looks like this. It's a gross exaggeration. Your lenses don't look like that, where the top is very flat. It's because it's nice and curved. If you take very small sections of your lens, every single section is going to be essentially flat. So what I do, if you take infinite little small sections of your lens, you're going to see here that our normal changes its angle. And that what that does, that allows the light to bend from going straight to bending and to bending more. This is what lenses do. They allow the light to focus, or either to focus on one spot. So here, this is to focus on one spot, or we can get lenses that make light rays move away from each other. Now you're going to say, but why would we want light rays to move away from each other? We do need light rays to move away from each other depending on the apparatus that we are using. So continuing from the diagram, we do have two types of lenses. We have converging lenses and we have diverging lenses. So let's read. There are basically two types of lenses. We have divergent and converging. Of these types, we have concave lenses and convex lenses. We have different types of convergent lenses. Convergent lenses usually are thicker in the middle, and diverging lenses are usually thinner in the middle. All right, so there's just some way to remember it. Convergent and divergent lenses, you have one makes light rays move together, one makes light rays move apart. Convergent lenses are usually called convex lenses, and diverging lenses are usually called concave lenses. All right, so these are just some examples of lenses that you all have. You just have to remember how to differentiate one from the next. How do you remember them? Convergent lenses are the ones that are thicker in the middle. If you look here, each and every one of them is thicker in the middle, right? And very thin at the edges. All right, so convergent lenses are very thin at the edge. Sorry, don't know why that happened. And diverging lenses are thicker at the edge, and thinner in the middle. So that's, how you remember them. Ray diagrams, a very important part of lenses. This is how we determine how your lens works. This is how they determine properties of a lens by using a ray diagram to draw out and to sketch out and to see how things work. So here you're going to have some terms that you need to learn. Quite a few terms, but you're going to realize are kind of self-explanatory. So we have a principal axis. Sorry. All right. Principal axis. This is an imaginary line that all points are taken from. So this is basically a line that we draw at the very start of doing ray diagrams. You're going to see just now, it's right here at the bottom. So we have our principal axis. We have optical axis. This is the point in the lens where light rays are measured from. So just to run it through you as you have the words in front of you. We have our principal axis. Our principal axis is just a line, a straight line that we draw, that we take all references from. Right? It's just a line that we draw. This kind of represents me a tabletop. Optical axis is this is the middle of your lens. If you were to take a convergent lens or a divergent lens, this line represents the middle of either lens. And this is the point where we take our measurements from. It's just a measurement, a reference line to know where you are measuring to and from. Optical center is the intersection of these two axes. So this will be your optical center. These are where those two lines meet. It's indicated by an O. Principal focus. This is the distance in, this is the distance in front of the lens and behind the lens where the light rays can act from. Principal focus is a point that exists both in front and at the back of the lens. Right? And this is where we take measurements from. Every single lens has different principal focus or foci, right? Because unique to each individual lens. Focal length. Focal length is the distance between your principal focus and your optical center, or your principal focus and your lens. So this is your focal length. Same distance in front of your lens. This is the front of the lens and the back of the lens. Why we say front and back? Imagine you are looking at a lens right now. This is the lens in front of you. So you will be in front of that lens, and what you see through this lens will be the back of the lens. Use that reference to you right now. Okay, so the front is where your object will be, and the back is where your lines and your light rays will mix together to form your image. So we call one side the front and one side the back of the lens. Object distance. Now, the front of the lens is usually where we place an object, and the back of the lens is usually where our image forms. So here we're going to have our object distance U, common U, is the distance between our object. So say this is our object here. The distance between the object and the lens will be your object distance, indicated by a common U. And somewhere our image is going to form. This is where our image is going to form. The distance from our image to our lens will be our image distance. It seems like a lot, guys, but it's the same thing you're going to be doing over and over. Then we have here object height. That is simply how high the object is. And then we have H prime. Right? H prime here indicates the height of our image. So just to go through our diagram here in more detailed points, Hold on, a whole bunch of people need to join. All right, so a more detailed version, we have our principal axis. We have our optical axis. Our optical center is where those two axes meet. We have our rays of light. Now, this is how it works. We have rays of light, and what they do, they all focus onto one point, and that one point is your principal focus. Okay, so that's how it works for convergent lenses. We'll do divergent lenses afterwards, right? And the distance between your principal focus and your lens. Someone's mic is on.
Sorry, Miss Andre.
Manish, you have more than one account logged in. Log out one, please. All right. Okay, so we want to now draw ray diagrams. Now, this is what our ray diagram. My mic is still on. Mute all. Okay, I've muted everyone. What happens during ray diagrams? This is what we have. We will have our object in, this is our lens. We will put something in front of the lens, and then somewhere behind that lens, an image will form. We want to know, the whole purpose of doing ray diagrams is to determine the nature of this image. This is our object. All right, so we want to know how far away that image is. We want to know how much the size of that image, and we want to know the nature of that image. We're going to go into what nature is just now. We want to know whether it's real or imaginary. Remember, we did real and imaginary images when we were doing mirror images. All right, and just to recap, a real image is one where you have one ray of light going from one point to the next. Anytime your light has to bounce off something, like here, this is one ray of light, that will create a real image. But the instant your light has to bounce off something, or your light has to go and change its direction, you're going to end up creating an imaginary object, imaginary image. All right, so this is basically what we're trying to do today. We want to determine how far our images will be, how large or small our images will be, and the nature of our image. So we have some drawing to do, and by doing some drawings, we can figure out what the nature of our image will be. So by doing this, yeah, next step, right? So what we have to do, we have to basically make a drawing like this, right? Where we have several lines coming out from an object, and you're going to have those lines meeting up at a certain point. And at this point where they meet up is where we create an image. So let's see what we have. When constructing a ray diagram, we need to note the location of two lines. It used to be three, but the third one is optional. But if you want to be extra precise, you can use the 3 lines. I am telling you how to do the 3 lines, by the way. So the first line that we have to draw, one, we draw a line from the very top of the object, parallel to the principal axis, to the lens, and then passing through the principal focus on the other side of the lens. That sounds like a lot. All right, so let's just read this again. We draw a line from the top of the object, parallel to the principal axis. So what we do, we have our object here, O for object. We draw a line from the very top, guys and girls. This is where we have to be very precise. If this is our object here, I don't want you drawing a line somewhere arbitrary in space. I don't want you drawing a line somewhere halfway down our object. You all have to be really, really accurate. Just draw a line from the very tippy top of your object. So you draw a line from the top of your object, parallel. You all should know what parallel means. These 2 lines are parallel to each other. You're going to draw this line parallel to the principal axis. Remember, this line here is your principal axis. This is your lens. and F is your principal focus. So you, number one, draw a line parallel to your principal axis, to your lens, and then you're going to take that line and pass it through your principal focus on the next side of the lens. Let's read that back. All right, so we're going to draw a line from the top of the object, parallel to the principal axis, to the lens, and then passing through the principal focus on the other side of the lens. So it's basically two lines you're drawing here. You're drawing a line parallel, draw a line parallel, you meet the lens, the exact middle of the lens, and you draw this down through your principal focus. So that's the first line. You draw this as far as you can. All right, and by drawing it as far as you can, that's your first line. Second line. A line is drawn from the very top of the object and through the optical center. And you have to draw it as far as possible. So what we're going to do, we're going to take a ruler. Of course, you need to do this with a ruler. You cannot freehand these questions, so please don't try to freehand them. So we're going to start from the very top of the object, and we're drawing a line through the very middle. Remember, we already noted where the middle of the lens was, and you're going to go straight down. You're going to go as straight as far as possible. All right, so that's the second line. Now, folks, when you all are drawing these, I'm going to put in some straight lines. And you are not precise with those lines, because we have some students saying, when you are not very precise, you're going to end up getting wrong answers. Your things are not going to work out right whatsoever. Let me see how to edit this. Hold on. All right. So if this was our line, let's just zoom in a little bit. If you now come and draw a line that's not passing through, as in it's just skirting. You see how it's just missing the middle here? You are not going to get a correct answer. If you go and take your line and pass it kind of a little bit at the bottom, I hope you all are seeing. If you pass it a little bit at the bottom of it, you're not going to get it right. So when you're doing these questions, you have to learn to pass through exactly through the middle of those two axes. Now, this is where having a sharp, dark pencil point is going to be helpful. See how this thick line kind of muddles up where that point is? Now, if I had used a thin line, where is it? All right, if I had used a thin, sharp line, you all would see exactly if your line is passing through the middle or not. All right, and you can see here it actually cuts a little bit more in front of the very center. My apologies, guys. All right, it cuts kind of in front of the section, in front of the axis more than the next side. So this is where, please be really, really exact when you're doing these diagrams, because how accurate your drawings are will make a difference. So those are our two lines, and we have to see where these two lines meet. Let's go through this again. I just spoke a bunch of stuff unrelated to each other. Our first line that we draw. That's colorful. One, from the very top of your object, you draw a line parallel to your principal axis. You meet the center of your lens, and then you draw your line down through your opticals, to your principal focus as far as you can. Second line, you draw from the very top of your object. You're going to pass this line through your optical center. You're all freehanding this with the button. All right, to the optical center and draw it down as far as you can. And where those two lines meet, right? If those two lines, wherever those two lines meet, as you see here in the diagram, it's where your image will form. So this is where your image will occur at this point here. And being here, we can now measure several things. We can measure using a ruler, we can measure the height of our object. We can measure how far away not height of object, height of our image. We can measure how far away our image is from the lens. We could even determine how much bigger our image is to our object. All right, so we have several things to remember. Now you all are going to get some homework on this. All right, I'm going to give you an example of each one of these where you have to draw it on your own, and you're going to see how different things happen with lenses. All right, so just to go through this, if I wanted to describe this image here, all right, let's take out all the excess writing. If I wanted to describe this image right here, right now, I'm going to be able to say a few things. One, my image is inverted. What does inverted mean? It's upside down, because if my object was right side up here, and my rays converge at the bottom of my principal axis, I can now say that my image is inverted. If you all pay attention a little bit, you're going to realize that my image is larger. It's slightly larger than the object. If you all take a look, you can actually see that. Let me see. Draw a line and we can compare it. Yeah, that should be about it. Right? Oops. So that was our object. Now, if you compare it to the image, you're going to realize that our image is a good bit, not good bit, but somewhat bigger than our object. So since our image is larger than our object, we call our image magnified. Remember, magnified means to look larger or to be larger. So here our image is inverted, it's magnified. And if we go back to what we were saying before about real and imaginary images, we're going to see here that one ray of light, as in the light did not bounce off anything, the light just got refracted, came from the object to form our image. So since one ray of light, as in nothing really happened to that ray, that light did not bounce off anything. Now when light bounces off something, we go from having a real image to an imaginary image. But since this light was only refracted and not bouncing off of anything, we can call this image real. Right? So usually when they ask you to describe this image, tell me something about this image, you're going to say, one, it's inverted, that's if it's upside down. Two, you're going to say whether it's magnified or diminished. Diminished is the reverse of magnification. And you're going to say whether it's real or imaginary. You know, real is when the light does not get reflected or bounces off something. Okay, so real images is when the light just moves straight from one point to the next. The instant they have to bounce off something, they're going to become imaginary. Remember, we went through why we have imaginary images. So you all are going to get homework on each one of these situations, right? And you're going to try them and see. So when you do the homework, I want to see if you all will get these 6 and if they match up with what you see here. All right, so please don't come and say, Miss, the lines didn't meet. They could never meet. Well, yeah, one of them will never meet. All right, so you're going to get some of these for homework and we'll try them. Now we're going to go on to the scale drawing part. Scale drawings are necessary to construct images that would otherwise not fit on a page. We have to draw this on a page. Sometimes you have to draw it on your exam paper. If your readings are more than 2 centimeters, if they give you readings of more than 2 centimeters, it is not going to fit on your graph page or on your notebook page or your exam paper. So here we have to now go and do scale drawings. You know, the scales that we were drawing in our graphs, guess what? They're back. They never left. We use them in multiple purposes, multiple places. So this is a simple process of reduction in scale factor. So in school, we'll do some examples on scales. Actually, no, we'll do some examples on scales right here as a couple of examples before you get your homework. Next part here, magnification tells us how much larger the image is than the object. Well, that's kind of obvious. If you have magnification, something is bigger than the next, right? When M, being your magnification, is more than 1, we have a larger image. And when M is less than 1, we're going to have a smaller image. So when M is more than 1, we're going to have a magnified image. And when M is less than 1, we have a diminished image. How do we work out magnification? There are 2 ways to work out magnification. First way, 1, it's going to be the image height divided by the object height. Or M is equal to H prime upon H. There's also another way to determine your magnification. It's going to be your image distance over your object distance. So either way, you can take one method or you can combine them to work out. Either one is going to tell you how much larger your image is than your object. Very simple way to calculate it, but you can also measure them when you're given drawings. Okay, so here we have some examples. All right, so you all are going to have to do this for homework, every single one of you. All right, we'll have to do it for homework because depending on the class, this is where we have all reached. Okay, so we have here, construct the following images, and for each, I want you to state the image distance, the image height, and the magnification. So what you're going to do, that's just really quick and simple. First thing, you draw your principal focus. Second thing, my tip to you, folks, when you're drawing this on a notebook page or a graph page, you want to use this in landscape mode, right? You want to use your paper, or you want to use your paper, your graph paper in landscape mode. You want to put your principal focus kind of close to the top of the page, right? So that's your principal focus. Oops. Right? Then you want to draw, so that's your principal focus. Now your principal axis. Now you want to draw your optical axis. Your optical axis, my tip to you is to draw the optical axis 1 centimeter greater than your focal length. No, greater than your object distance. Your object distance here is 2 centimeters. We do an example. So if your object distance here is 2 centimeters, I would draw my lens about 3 centimeters from the edge of the page. So that's going to give me a lot of space to work with on your page. If you go and draw your lens in the middle of the page, sometimes this is going to happen. You're going to have your object here, your image is going to be here, and then your image is end up going to form outside of your paper. So my little tip to you, always draw, look at where your object and images are, right? And you draw to suit. So if my object here is 2 centimeters away from my lens, draw the lens probably about 3 centimeters away from the edge of the page. So that means you have a lot of real estate on your paper to use, right? So we have here, focal length is 1 centimeter. So you're going to put 1 centimeter in front of the lens, 1 centimeter at the back of the lens. This is how you should write it. You draw your image. How high is your image? 1 centimeter. So once you have these things down, you know the image distance is 2 cm. You know this is 1 cm high. You go ahead now and draw your lines. What are the lines we have to draw? Let's go through that again. All right, we have 2 lines to draw. 1, we draw a line from the very top of our object, parallel to our principal axis until we meet the lens, right? And then once it meets the lens, the very middle of the line here for the lens, we're going to take that line and pass it through our principal focus. All right, so that's our first line that we draw. Our second line that we draw, let me put a proper shape. The second line we draw, we're going to have to take from the very top of our object to the very middle of our lens and draw it straight through. All right, draw it as far down as you can, and wherever these two lines meet, the very middle, so here you have to kind of estimate where the two of them meet. This is where your image will fall. So that's how you do your drawing. I'll go through this several times, don't worry. So here, this is where you can measure how high it is. You can measure how far away from the lens it is. And then you could go ahead and calculate the magnification. How do you calculate magnification? There are two ways, H prime over H. I know H here was 1 centimeter. I can measure what H prime is. Or I can go and do two ways. I could go and measure my image distance divided by my object distance, and I will get my magnification. All right, so you're going to have to do these several times. So let me just write down an example. So we're going to pull up some graph paper. I'm going to show you how to do a few on the graph paper. That's now. Let's see what we have. I don't want to take numbers that you have from the homework. That'll just be me doing your homework. That's not fair. All right, so let's pull up some graph paper. Hopefully I can find some graph paper. Blank graph. All right, so we have some graph paper here. Let's go ahead and try this and see what we can get as a scale drawing. Now, sometimes you don't need the entire graph page to do a drawing. All right, but we're going to use as much as we can to do our drawing. All right, so this is our graph paper. This is exactly what you're doing at home when you're going to be doing a question. Now, suppose I have a question where, right, my object distance is equal to 3 cm. My focal length is 2 cm, and my object height is 2 cm. Now you all should know the distance between the dark lines and the graph pages are 1 centimeter. So it comes in really handy when you have to draw your lines. So let's go ahead and draw our graph right now. Now draw our ray diagram. So the first things first that we put down is our optical, is our principal axis. Put it in something you all can see. Okay, you can see the orange. All right, so that's your principal axis. You choose where you are drawing it. Then we want to draw our lens. The second thing we have to do is draw our lens, our optical axis. I said here, remember I said if you look at your object distance, let's just revise, U is your object distance, V is your image distance, F is your focal length, H is your object height, H prime is your image height. I'm gonna go through them over and over. By the time we finish, you will know all these letters very, very simple, very quickly actually. So if I said my image, my object, my apologies, my object is 3 centimeters away from my lens, I can probably put my object right here. Let's put our object down. I can put my object at the edge here. Really exact and precise. Let's put this a little thicker. Right, so that's my object, and my lens is 3 centimeters away. So let's draw our lens. Obviously, this is faster with pen and paper. 1, 2, 3. Let's go a little bit outside of the graph. Let me just myself a lighting. All right, good. Easy for us to see. Okay, so we have our principal axis. This is our principal axis. This is our optical axis. Let's draw our 3 lines. Oh, and we have to do our principal focus. Our principal focus is 2 centimeters in front of the lens, 2 centimeters in the back of the lens. We put a little F to represent them. Let's draw our lines. First line that we have to draw. We're going to draw from the very top of our object, parallel to our principal axis, to the lens. And then what we're going to do, we're going to take this line, and then we're going to make it pass through the principal focus. So we go from the very optical axis, and we draw as far as we can. Oops. Draw as far as we can while passing through our principal focus. So that's our first line. All right, what is our first line? From the very top of our object, the very, very tippy top of an object, parallel to the principal axis, we hit the lens, and then we go down through our principal focus at the next side of the lens. We draw as far down as possible because we don't know where it's going to meet the next line. Now we look for our next line. What's our next line? This is our first line. Our second line, if you recall, is from the very top of our object through the optical center of our lens, and we draw it straight across. I don't know if this is going to meet on this page because I probably took too small for space, but let's see if we get lucky. All right, so from very top through the optical center, so I'm going to take, this is where you need a long ruler. You cannot do this with a short ruler, folks. Question?
It is.
Right? So we go from the very top of our object to the optical center, right? And we draw that line straight across. And wherever these two lines meet is where our image is going to form. Right? So again, this is why we need to have very sharp, dark pencil points, because when you have two really thick lines, it's kind of hard to estimate where they meet. Right, but let's see if we can estimate where they meet here. Right, where they meet is about, yeah, let's take the exact middle. It looks about there. Yeah. Right, oh, I see changes upside. Where is it written right in the middle? All right, so that is where our image will be. Now we want to take measurements of this image. How do we take measurements of the image? Number one, you can take your ruler and you can measure how high this image is. Take your ruler and measure how high it is. So here, since we're using graph paper, we can check it could be 1 centimeter, 2, 3, 3.5. Right? 3.5 centimeters. So that will be my image height. I want to see how far away my image is from the lens. So that's going to be this distance here. Right? It's just the horizontal distance from the lens. Right? And if we check, that's going to be 1, 2, 3, 4, 5, 6.5. So that means this is your H prime, my apologies. Your image distance 1, 2, 3, 4, 5, or 5.5, 5.5 centimeters. And if I want to work out what my magnification is H prime over H. And here it's going to be 3.5 over, what is my height? 2. So that's going to give me 3.5 divided by 2 is 1.175, right? 1.75, or we can use the next direction. We can see how to work out your magnification using your V over U. And V over U is what? 5.5 divided by 3. And this is going to give me 1.2. 1.8 something. Four, 5. All right, 1.85. Now you will get slightly different numbers depending on your accuracy. Now see here, since I didn't draw it exact, my accuracy is probably off by a little bit, but you all can try it and be really, really exact with your drawings, and you should get it out pretty okay. All right, let me just make sure. Yeah, 1.8. All right, so let me just clear the board of all the writing, and we'll just do this drawing from scratch. And you all should get it because you have to do all of these on your own. It's clearing all the writing here. Sorry if the image is flickering. Right, so I want to do my ray diagram drawing. We have to look at the numbers that we've been given and draw our diagram. So when we have a ray diagram drawing to draw, they usually give us our object distance, our focal length, and our object height. You draw your, number one, you draw your principal axis. You draw your principal axis, that's this line here. Number two, you draw your optical axis, that's the vertical line here in yellow. And the very center here will be your optical center. 3, you draw your object. And there are 2 things you need to know when you're drawing your object. You have to know how far away your object is from your lens, and you have to know how high your object is. So that's the 3rd thing you do. The 4th thing you have to do, you have to draw your 2 lines. What are our 2 lines again? Line 1. From the very top of our object, we have to be very precise, folks, as in you wouldn't believe the difference a little 0.5 millimeter makes. It makes a difference when you're doing these questions, especially when you're kind of off. All right, so you draw from the very top of your object, parallel to your principal axis. You meet your lens, so you're going to go parallel. You meet in your lens, and when you hit your lens, you have to pass through the principal focus that is on the next side of your lens. Remember, the principal focus is in front and behind your lens, and as your focal length here tells you how far away it is. So you go through that point and you draw your line as far down as you can. Please don't come and say, Miss, I didn't get the line to meet anything, but you went and just drew a line up to here. Oh yeah, that makes no sense. It makes no sense whatsoever. Or I have seen students do this. They draw the line right up to F. You don't draw it right up to F. It has to pass through F and go as far down as possible on your paper. All right, so it goes far down as you can. Your second line that you draw, it has to start from the very top of your object, pass through your optical center. Remember, this is your optical center. You draw that line as far down as you can. All right, and where those two lines meet is where your image will form. So this will be your image here. Since your image is below your principal axis, it is obviously going to be upside down. So that means if it's upside down, your image is inverted. Here you can see, obviously you all can see that your image is larger than your object. So your image will be magnified. And if I wanted to describe the image, one ray of light leaves my object and forms my image. One ray of light, as you all can see, there's one line went down to form your image. So that means that your image is a real image. It's not virtual. All right, and then you could go ahead and take your ruler and measure. So then 5, you can do your measurements. What are the measurements you can take in this? You can measure your image distance. You can measure your image height, and then you can go ahead and do any necessary calculations. What calculations can you make from this? You can calculate your magnification. All right, so when you all are trying this homework, now you all are doing the 5 questions that are in this sheet. I'm going to post up the questions separately in case. All right, it's difficult for you all to find in the handout. I'm going to post them up for you, and you all have this week to submit them. Well, not to submit them, to compare your answers. If you did not get it right, then you're going to know that you didn't get it right. If you were getting some problems, you will have to tell me that you're getting problems with them. Next day, you all are in school, so form 5s. I see you tomorrow. If I were you, I would try a question today at least. Try 1 or 2 drawings today, so you can bring them for me tomorrow when you come to school. So that would be group B in the 5-6 and the entire 5-5. Right? You'll bring that for me to see tomorrow. No, wait, even the form 4s, I see you all are in school tomorrow. All right, so you can bring up your stuff for me tomorrow just to check. If you get any problems, we can go through it. Now, folks, if your diagrams are not precise, you are not going to get accurate answers, right? A little difference makes being off by a little bit makes a big difference in these drawings. And you'll see them when you try them. All right. Any questions so far? Are we okay? Hit me a thumbs up or correct if you're okay so far. All right. I see 1 thumbs up, 2, 4, 6. Is it reading? It's reading. All right, good, great. All right, so we're going to move on. Right. So we want to move on now to some scale drawings, or how to do your scale drawing, because I just said that sometimes you all are going to have numbers that are too big to fit on your graph page. Right? Like here. Right, I'm going to show you. If you have a question like this one here, where your U is 20 and your F is 15, that is not going to fit on your graph paper. You could join like 6 graph pages and hopefully it's going to fit on the same paper. So let's see how we can work out what a scale drawing is. It's raining by anybody? I know you're pretty close by. All right, so suppose I have u is equal to 25. F is equal to 10. And H is equal to 20 cm. And I want to draw this on my graph paper, right? To fit these numbers on your graph paper, if you all know how big your graph paper is, you already know that this is not going to fit on your graph page. It's going to be too small. Being your graph page is going to be way too small to accommodate this image. So what do? We come up with a scale, just like what we do in graphs. A scale is simply a set of numbers or a way of shrinking down our numbers to work on the graph page that we have. And in this case, how do we determine the scale? We find our HCF, highest common factor. Now here your highest common factor could give you a fraction too. So anybody, the most obvious one is not going to be your highest common factor. There's a smaller one. Anybody in the chat or by voice, what common factors do we have in 25, 10, and 20? Let me hear you all. We unmute the class. All right, anybody? I see 5. Yeah, 5 is a HCF, but I can get better than that.
Ten.
I have 10. I can get better than that. You could get even bigger than 10. Yeah, you can get 20. All right, but 20 is going to give you a weird number. 10 is going to work out best, but 20 can also be used in case your drawing is really, really big. Now, how is this 10 going to help us in determining our scale? So first things first, I'm going to write on the steps to the side. Step 1, you find your HCF. So 2, how do you determine your scale? You divide every number by your HCF, and those are going to be your new readings. So since your HCF was 10, our new readings will be what? Divide each number by 10. 25 divided by 10 will be 2.5. So your U on the drawing will be 2.5 centimeters. 10 divided by 10 is 1 centimeter. So that means on your drawing, your focal length will be 1 centimeter to draw. And your height of your object, 20 divided by 10 will be 2 cm. So if you see, these numbers are kind of similar to what we had before, and it's going to now fit on our graph page. But please, you all have to be careful to convert back when you are done. So third step, draw as normal. Let's get rid of this one. So let's draw this and see what we're going to get. Height is 2 centimeters. So you want this to be 2 centimeters away. Let's put in our lines. Now, if you all want to start pulling out a graph page and try drawing them, you can go ahead, you know. I don't think we'll have that much time. Let's make this lighter again. Right. So that's our principal axis. We want our lens to be at least as far away as our object. So since our object is 2.5 centimeters away, you know, we can put our lens probably 3 centimeters away from the edge of the page. It takes practice to determine how far away you're going to draw your lens. All right, I will guide you all in the start. So that's going to be my principal axis. This is my optical axis. You don't need to write PA and OA. I'm just, showing you for now. My object is 2.5 centimeters away from my lens, and it is 2 centimeters high. So let's see where 2.5 centimeters is. Let's get the arrow. 2.5 is about, this is 1, this is 2, 2.5 is about here. And it's 2 centimeters high. Right, so that's my object. I know that my principal focus is 10 centimeters, or when you use your scale, it's 1 centimeter on your drawing. So where is my principal focus going to be here? This is my first principal focus on the front of the lens, and my second principal focus at the back of the lens. So, and we know that our optical center is where our 2 axes meet. We can make our drawing now. So let's do our first line. Our first line is we draw from the top of our object, very tippy top of our object, to our lens. All right, so that's the first part of that line. And then we have to draw from the, you see already how I kind of at a little angle. So I'm gonna have a little bit of problem being accurate. I hope you all see that I already drew it a bit of fun short angle. Just so. So the next line we have to draw is from the very top here through our principal focus, and we go down as far as we possibly can. So you make sure and pass through your principal focus, and you go down as far as you can on your page. Did I pass through? Yeah, kind of off a little bit. Right, so that's the first line. Second line, what's the second line? We start from the very top of our object through our optical center, and we draw it down as far as we can. So let me just zoom back out because it's hard to see where the stuff is from so close. So from the top, we pass through our principal, through our optical center, and we're going to get our object happening. Yeah, image happens here. So I'm sure now we can see where these 2 lines meet. We could go ahead now and draw our image. Our image is going to be exactly where these 2 points meet here. So you draw, take a ruler, you draw your line. Now here, please use a ruler. Do not come and draw this. I'm going to see somebody doing this. Y'all, no, don't do that. Be very precise. It has to be 90 degrees to where we're drawing. So let me just estimate because I'm doing it backwards. Yeah, that will work. The arrow's a bit weird. Right, and that will be your image. So this is where our image will exist. And now you can go ahead and take measurements for your image. What are the 2 measurements you take for your image? 1, we measure how far away it is from the lens. So here we can see that the image is 1 point, it's a little bit over 6, but we can say 1.6 centimeters. Don't worry, we have something with the scale to bring into consideration. So V is 1.6 centimeters, a little over, but we try our best. 1.6 centimeters away, and then we can measure the height of our image, and it's going to be 1.2 for 1.3. centimeters high. No, it is not actually 1.3 and 1.6. Remember, this is a scale drawing where every centimeter here actually means 10 centimeters. So since our scale drawing, so our scale is 1 centimeter, represents 10 centimeters. See how it's just like how we do in graphs in school? That means we have to now go and multiply each of these values by 10 to see what it actually is. So since our scale value is 10, no, each centimeter means 10 centimeters. So 1.6 centimeters will be 16 cm. And 1.3 centimeters will actually be 13 centimeters. So if you have to work out this question, you can now say that V is equal to 16 cm. H is equal to 13 cm. You can now go and work out your M, and we could describe the nature of this image. Let's see what the nature of this image is. 1, is our image right side up or upside down? It's upside down, so it's inverted. 2, is our image larger or smaller than our object? Anybody? This is our image. This is our object. Is our image larger or smaller?
Smaller.
Smaller. So since our image is smaller, we call this image diminished in size. And 3, is this real or imaginary? See in the chat. Real, very good, because remember, real images form when the light moves in one direction and it just gets bent a little bit or gets refracted. Refraction is fine for real images. It's when your light goes and bounces off something, then it becomes imaginary. Our light didn't bounce off anything, it just got redirected a little bit. So that means we can classify our image as being real. So when you all do questions like this, we ask you several things. We ask you, 1, to work out your V, to work out your image height, to work out your magnification, and then to describe the nature of your image. So anytime you all do these drawings, get in the habit of writing them down all of these, because you never know what they're going to ask for you in exams. And it's best that you learn how to, identify everything from your questions. So that your homework here, let's just scroll back up. Did your homework disappear? Or the homework is at the bottom. All right, so you have some homework here. You're going to go ahead and use, do ray diagrams and work them out. My little tip to you, question 1 is definitely 1 and 2. You don't have to use scale drawings, but you all can see here 10 centimeters, 20 centimeters. This is your trick question. Right? These here you will definitely have to use scale drawings. So I will put these back up on the as a separate document for you all to use, so it's easy to find rather than going through the entire handout. All right, I might probably add in another scale drawing one just for the practice. Concave lenses, we will do another day. I want you all to draw your images first, and then we will look at concave lenses. All right, hold on. Now, we can work out everything in a lens, right, by drawing, or we can go ahead, folks, and calculate it. Everything that we just did in the diagrams and in the drawings, we can calculate it. So let's read. Everything that was done above can be achieved by calculations. Of course it can, but this is physics. Physics, we can do everything by calculation. Every single thing by calculation. And the next lab that we are doing, for light will be to determine the focal length of a lens, and our formula for focal length is 1 over f is equal to 1 over u plus 1 over v. Now here you're going to have to use fractions. Pretty sure somebody we're just joining a meeting. Pretty sure that everybody here knows how to use fractions, but we're going to have to be very careful and check them. So let's see. 1 over f is equal to 1 over u plus 1 over v, where f is your focal length, u is your object distance, v is your image distance. And care must be taken with these calculations since fractions are being used. Now, let me just go through what is the importance of focal length. Focal length tells us how much we actually cause the light to diverge, right? When we have, say, an image with a small focal length, that means it's going to make all the light rays diverge or to converge very close by. So if this was our light and we had a really small focal length, it's going to converge very close by. If we have a large focal length, that means light is going to get deviated very, very at small angles. That means they're going to converge much further away from each other. So focal length tells us how powerful our lens is. It tells us how much light bends by passing through our lens. For those of you all who wear glasses, you all have different focal lengths for your glasses. That's how we can determine. I'm pretty sure you all, next time you're in class with one of your classmates, and if you all have different degrees in eyesight, take a look at your glasses, and you're going to see that, or compare with somebody with the next glasses, you're going to see that the light bends differently in your friend's glasses than yours, because your focal length for your glasses are different, because your eye problems are probably different. So we have here focal length, object distance, image distance. And then again, we just went through this. Magnification, we can calculate. So we have a couple more questions there, but let's just go ahead and try these. This is where you all need to have your calculators out. Now suppose here, let's try an example. I want you to find f when u is equal to 4 centimeters and v is equal to 12 centimeters. I want to find my focal length. My focal length is going to be 1 over f is equal to 1 over u plus 1 over v. So where I see u and v, I plug in my numbers. So I'm going to get 1 over 4 plus 1 over 12. People, is this equal to 2 over 16?
No.
No.
Almost.
No, this is not how we add fractions. But guess what? One of you, being somebody in these 3 classes, will do this. Will do this. I can guarantee you that. Right? Because people will just go see blind numbers, add it up and go, but they feel, people, pretty please, these are fractions. Yeah, Emmanuel, come into that. Those who try working it out, come into that. All right, so let's go and add this the way we can add it up in fractions. How do we add fractions again? We find number 1, our LCM. The LCM of 4 and 12 is 12. We check our fractions. 4 into 12 is 3. 3 by 1 is 3. 12 into 12 is 1. 1 by 1 is 1. So you're going to end up with 4 over 12 or 1 over 3. This is not our final answer because this is telling us what 1 over f is. So if 1 over f is equal to 1 over 3, all we have to do here, folks, is invert our numbers. So you're going to get f is equal to 3 centimeters. Let's try another one right here at the side of the screen. if the length. Suppose I have u is equal to 40 and v is equal to 280. We do have that happening. I want to now go and work on my focal length. Right? So 1 over f is equal to 1 over u plus 1 over v, which is going to be 1 over 40 plus 1 over 280. Now, if you're using your calculators, you can use this on your calculator. Everybody, if you have your calculator out, but we'll try this in school, you can go ahead and use the fraction function in your calculator. Your fraction function in your calculator usually looks like this. Have you all ever seen this button on your calculators?
Yes, miss.
Yeah. So you can press 1, ABC, 40, plus 1, ABC, 280, and hit the equal sign. And you all should get 8 over 280. Anybody? I'm checking it too. See something in the chat. Yeah, it's going to break it down. So you're going to end up getting 1 over 35. Anybody get 1 over 35?
Yes, miss.
1 over 35. And when you work out the 1 over 35, that's not your final answer. That means 1 over f is equal to 1 over 35. So that means f, you just find the input. So 2 will be 35 cm. Right now, in exams, they're going to ask you to do either one of these versions. They're going to ask you to calculate your focal length and your distances, or they're going to ask you to draw your stuff. You have to know how to do both. But when you're doing the drawing, you know what? You can always just use the calculation to make sure that you're correct. And obviously, we'll never get as precise as the calculation because being people, we can be off by a little bit. Right? So what you're going to do, let me just zoom out a little bit. So what you're going to do, in addition to the questions that you all are going to have to draw, you're going to now go and work out everything by calculation. Right? Just to double check what you have done. Now, a little tip here. Let me just do one from the opposite direction now. Let's just get some meeting space. Now, suppose I tell you, these example 2 on calculation. Suppose I tell you the focal length of something is 10 centimeters and my object distance was 12 centimeters. And I want you to go ahead and calculate V. When you're doing this, you're going to have 1 over F is equal to 1 over U plus 1 over V. Here, you're going to have to go and do some subtraction and jumping over the equal sign. So here, you're going to have 1 over 10 is equal to 1 over 12 plus 1 over V. Let's bring the numbers together. So this 1 over 12 is going to get subtracted on the next side. So you're going to have 1 over V is equal to 1 over 10 minus 1 over 12. If you work that out, you should get, let's check this quick, LCM of those two. 6 minus 1 over 60. Anybody who's working it out, The LCM of 10 and 12 is 60. 10 into 60 is 6. 12 into 60 is 5. 5 by 1 is 5. 6 minus 5 is 1. So you're going to get 1 over V is equal to 1 over 60. You just find the inverse. So your image distance will be 60 cm. So if you get your image distance to be 60 cm, you could work out your magnification too. That's going to be V over U, which is 60 over 12, which is equal to 5. All right, so you all keep note, take note of how you do your calculations for these things. Do not just go and blind say you added numbers, right, and whatnot. Sometimes you have to subtract a number. Sometimes something has to go across the equal sign and become negative, right? So be careful on how you do your calculations and see what they want from you. All right, so look out for some questions coming up, but of course, everybody who is here, right, or who's looking at the recording, please try those drawings. Those who I'm seeing tomorrow, you don't need to do all, but you know what? I used to really enjoy doing ray diagrams, and I would do as many as I can. So if you start doing some ray diagrams today and you like doing them, do out all. I'm going to post them up in the next 10 minutes or so, right? The questions for you all to try by both drawing and by calculation. All right, so that's going to be the end of this class for here. That's going to be the end of our recording. We are not doing these questions yet. That's here. We'll look at that afterwards. So that's to see what will be the next class recording. The next class that we'll have online, we're going to look at color. I think the handout finishes here. The electromagnetic spectrum. And then after that, we're going to go into the eye. All right, so that's going to be our next class. So that's if you want to read it up, the eye and stuff is our next handout. We're going to do color for our next online class. We're going to do color, electromagnetic spectrum, the eye defects, and how we fix them. All right, so we're going to stop the recording here. If I can find it.